Welcome to today's IEEE Geoscience and Remote Sensing Society webinar. We're so glad you're joining us. United by the mission to advance geoscience and remote sensing, GRSS is dedicated to knowledge sharing by ensuring transparent, accessible, and collaborative learning for all. And our webinars are just one way we bring that commitment to life. Designed for students, early career researchers, professionals, and enthusiasts. These webinars address foundational topics as well as a wide range of emerging subjects, while also offering sessions on academic writing, publishing, and career planning. Our webinars are made possible through the collaborative efforts of GRSS's technical committees and various other initiatives, bringing together a diverse community of experts to deliver high-quality learning content. During the webinar, please submit your questions through the Q&A feature, and they'll be addressed at the end. You'll be asked to complete a survey afterwards, which helps us tailor content to your interests. Be sure to check out the IEEE GRSS YouTube channel for previous webinar recordings in case you missed any. And for updates on future webinars, visit the GRSS calendar and follow us on social media. We're excited to have you with us. Let's dive in.
Hello, everyone. My name is Dr. Adnan Siddiq, and I'm the chair of REACT Technical Committee. As you just heard in the introduction video, GRSS has several technical committees, and REACT is one of the 9. It stands for Remote Sensing for Climate Change, for Remote Sensing Environment Analysis for Climate Technologies. And as you know, we have this webinar series. We continue to organize these webinars throughout the year. For 2025, today's webinar will be the last one, but not the least. In 2026, we again start with a new line of speakers. Today we have Dr. Carolina Hurtado-Pulido. She's an expert in land subsidence mapping using SAR and other technologies, and she has done some wonderful work. And I would like her to share with us her findings, and this webinar would continue for about an hour. So we would have like 45 to 50 minutes of this talk, and then we will have about 10 to 15 minutes of Q&A time. So please use the Q&A option to submit your questions. Yeah, that's all from my side. Over to you, Carolina.
Thank you, and thank you for inviting me. So, well, I am going to start to share my screen. Okay, can you see my screen in presentation mode?
Yeah.
Okay, thank you. I am going to, sorry, wait a second. Pointer. In here. Okay, so today, well, first, thank you for inviting me to this presentation. Today, I am going to talk about land motion and large data sets. And okay, so first, I am going to talk about land motion. And in this image here, you can see that.
Carolina, I'm sorry to interrupt you because I made a mistake. I forgot to introduce you properly with your affiliation. So I'm sorry about that. So okay. For all the participants who are listening to us, with apology, Carolina Hurtado-Pulido is a postdoc at Purdue University in Professor Andrea Donnellan's group. And she has been working on land motion measurements with, as I said before, with different sensors, particularly SAR. And now over to Carolina again.
Okay, thank you.
Yeah.
So, well, first we are going to talk about land deformation, land motion. So you can see in this image that a lot of stuff is happening. And because of this, the land deformation, land motion is a big issue, can be a big issue to quantify. So first, it has different depths. So total land motion is the result of all the processes that is happening and all the different depths below ground level. Also, the nature of the process, it can be natural driven, like a natural loading, or processes like air cross and mantle dynamics, but also there are processes that are caused by human activities. Also, the spatial scale. So land motion can have drivers that occur at very local spaces, but also at regional spaces. And finally, temporal scale. So there are processes like fluid extraction and even some tectonic processes that act immediately or at short time scales. But also we had processes like lithospheric sediment loading that act in very long times, so geological times. So you might wondering why we care about this. So what happens if we have land motion? So in particular, I have worked in coastal areas, and land motion has a strong effects in coastal areas. In here, you can see three different concepts. The first one is absolute sea level rise. So this happens when basically we have a volumetric changes in the ocean, and processes like ice melting or water expansion can cause sea level rise. We also had a vertical land motion, and basically is the motion of the ground, and it can be subsidence, so basically the ground is moving down, or it can be uplift, so the ground is moving up. And we have relative sea level rise. So relative sea level rise is the effects of both of these processes together. And this is basically like a better metric to quantify how much basically inundations and sea level rise is a threat for coastal areas. So let's talk about the land motion in the Gulf of Mexico. And some areas in the Gulf of Mexico have been my study areas for the last few years. So this is the coast of Louisiana, and here is New Orleans. And you can see in all these images that subsidence in the area and relative sea level rise has been studied in different in different investigations in here, because basically here we had many factors causing subsidence, and is an area that is highly affected by sea level rise. So in here, I am showing you a cross section of South Louisiana. And I am going to talk about the processes that cause subsidence in here. In this area, you can see in red the location of Baton Rouge, and in blue the approximate location of New Orleans. So the first natural process that I am going to talk about is faulting. So faulting in the long term can be is a slow process. So basically, like when we compare this process with other process, it is slow in the long term geological terms. But in some areas, in some places, it can be fast if there is recent slip. And also, we have compaction of sediments. So compaction, on the other hand, is a fast process that can last like maybe a few decades, and is one of the main processes causing subsidence in the area of coastal Louisiana. We also have other natural processes like isostatic adjustment, glacial isostatic adjustment, and sediment isostatic adjustment. And these processes are slow. They act on geological time scales. So what happens in here is like basically we have a ice chip in the area, in an area. We have subsidence under the ice and uplift in the area around, in the periphery and beyond. So you can imagine that the study area is located around this area in here that I am pointing in the periphery of the ice sheet. So when the ice melted, there is rebound. So this rebound is uplift, and there is subsidence in the area that used to be uplift. Also, we have anthropogenic processes, and some of the main processes causing subsidence in the area caused by human activities are extraction of fluids, groundwater, and hydrocarbon production. So what is happening here is like in aquifers and the reservoirs, before extraction, all the pores are filled with fluids. But after extraction, the pores are empty, and there is compaction of the reservoirs or the aquifers. And after compaction, there can occur a subsidence. Most of the time, this process is considered fast because it acts in a few years or a couple of decades. And also it is very local, so you can observe a subsidence very close to the area of extraction. So how do we measure land motion? So in this figure here, I made this figure using Copilot and Site AI. And I use the prompt, what tools are used to study land motion. And you can see here all the different methods that can be used, and the number are the number of publications that the system found. I think this is an underestimate of the number of publications, but still you can see a trend where GNSS, INSAR, and LiDAR are highly used. So why are these methods are so popular? So they have some general advantages. They are open source most of the time. There is a lot of data that is open source. Also, there are open source software options. There are communities behind supporting the learning and the processing of the data. And in general, these are considered large spatial datasets. These are considered large spatial coverage. I wanted to highlight that Grace is also like in this category, but I am not going to talk about Grace because I don't have much experience about this one. So I am going to be talking about GNSS, INSAR, and LiDAR. Also, we need to be aware about what we are measuring. So most of the time we want to measure ground level subsidence, but we had many stuff in our surface. So we had different kinds of buildings. So in this example, you can see these buildings that have different foundation depths. So if we go to this one that has a deep foundation, if we measure subsidence in here, it is going to show only a small fraction of the ground level subsidence. But if we measure a subsidence in the building in this building that has not foundation, it is going to show even more subsidence because it's going to show the ground level subsidence and it's going to show subsidence caused by the load of the building itself. So we need to know what we want to measure and what we can measure. So to do this, we need to understand what method is better for this and understand what the method is actually doing. And also something that is something important here is that all the measurements are relative. So we need to be aware of the reference frame and the reference point that we are using for our measurements. So the first tool that I am going to use, I am going to talk about today is INSAR. And INSAR is very popular to measure land deformation. So in this image, you can see like the basics of INSAR. So first we have the satellite taking information, taking the image. And the first image, we are going to call it a reference acquisition. So it measures the signal between the satellite and the object of interest. In this case, this is a rock. Then we have a second acquisition. And ideally, these two acquisitions are taken from a similar point of view. So when we have the second acquisition, we are also measuring the signal between the satellite and the rock in this case. And you can see that there was a change of the location of the rock. So this change is measured as a phase change because INSAR is not measuring land motion per se, but it measures phase change that we can basically translate into land motion. And then, well, I have here a basic workflow to process INSAR time series. So we need a set of unwrapped interferograms. So an interferogram is formed by two SAR images. And it is showing us basically the motion between these two SAR images. So in this case, blue is subsidence and red is uplift. When we have our set of interferograms, we need to create a stack of interferograms. In this case, we have an image that is the reference for all the other images. So all the other images are aligned with this with the reference acquisition. Also, we need to have a reference point, and a reference point is a point in the area that should be stable over time. And we at least need to try to know how the reference point is moving so we can do later corrections for this motion. And also, we need to perform some corrections. So when SAR is measuring phase change, it doesn't measure only the phase change from the land motion. It also has contributions for other processes like atmospheric delays and Earth curvature. So we need to perform these corrections. And after that, we can have the displacement time series and the velocities. So some of the advantages of INSAR are the data options that we have. So you can see here that there are many satellites. Well, many satellites have been launched since 1980. And there are many bands, different options for these data sets. Not all the datasets in the not all the satellites in the image in the figure provide open source data, but many of them do. So MBSat and Sentinel-1, for instance, they provide open source data. And these two satellites are part of the European Spatial Agency. And so we have open source data repositories. So I put here some of the popular ones. So AESF, that belongs to the University of Alaska Fairbanks, has a large repository of images, SAR images from different satellites. And also sometimes they provide some products already processed. And so we have the Copernicus browser that belongs to the European Spatial Agency. And in here you can find information from Sentinel-1 and MBSat. And we also have Opera. And Opera is an initiative that belongs to GPL. And in here you can find products that are already processed for the US, and some products are also for global use. Another advantage that we have about INSAR are the open source software and community. So in here, ICE, GMT, SAR, and MinPy are Python packages to process INSAR stacks, interferometric stacks, and INSAR time series. Also, Earthscope provides basically resources for education and workshops. So sometimes they create workshops online to train people on these Python packages. But if you cannot be there, you can find the workshops recordings online on YouTube. And also SNAP is another software that belongs to the European Spatial Agency, and this one works to process Sentinel-1 data. Also, INSAR has some challenges. So the first one is computational requirements. So in this figure in here, you can see a screenshot of my dataset. So each INSAR image is more or less 7 gigabytes. In my case, I am using 224 images. That is more than 1 terabyte. So you need a large storage space because you are going to save the data, the raw data that you are using, but you are going to need at least the same amount of memory to store to save the results. Also processing power. In my case, I am using Purdue supercomputer. And processing time. Time can vary depending on the number of images that you are processing, but also the size of your study area and the features of your computer. Other challenges include the correlation, graphing, and atmospheric errors. So I'm here, I am using a picture from the coast of Louisiana, one of the marshes, and you can see here a lot of vegetation. Vegetation can cause a lot of the correlation errors because basically the vegetation is growing faster than the periodicity of the images. So we cannot record vegetation changes with INSAR, so it's going to cause errors. Ungraphing errors are sometimes caused by water bodies, so big water bodies can be also a problem in INSAR, and atmospheric signal. As I mentioned before, we need to apply corrections for this signal because sometimes it is a big source of errors. And the other challenge is the reference and validation points. So INSAR needs a reference point, and ideally we know how the reference point is moving. So we can use a GPS station, a permanent GPS station as a reference point. And if we can, we should validate our results from INSAR with other GPS stations. But you can see here that some areas in the world don't have many GPS permanent stations. And actually, if you zoom in, the density is not that big in most areas. The other tool that I am going to talk today is LiDAR, specifically airborne LiDAR. So in this case, the sensor is attached to the airplane, and the sensor sends a signal and measures the time that the signal takes to hit again the sensor. So we can translate this time into distance between the airplane and the surface. So basically what we want to do in this case is, if we have two LiDAR surveys, we want to know what is the separation in the vertical and horizontal components. And with this, we have land deformation, land changes. And we can do this with several methods. So I have used the iterative closest point in here that basically is aligning the point clouds per se. But we can also do vertical depth differencing. So in this case, we create a digital elevation model for each LiDAR point cloud, and both of the digital elevation models should have the same pixel size. So in this case, basically, we do pixel by pixel differencing. And the result is a digital elevation model of differences. So in this example in here, for instance, you can see blue areas that will be a land motion going up. So basically is gaining more surface, or in the red areas indicate that is going down, or subsidence. Some advantages and challenges. Well, in terms of data, the data sets usually are not that dense compared with INSAR, but there are some repositories like Open Topography that has a big data set of LiDAR surveys. So if you are curious, you can go to Open Topography and see if your area has some LiDAR survey. So JEDI is not urban LiDAR. Actually, JEDI is a sensor that is attached to the International Spatial Station. And I haven't used it myself, but I think it will be interesting to use it for these purposes. Also, in terms of server community, PIDAL and LAST tools are packages designed to work with LiDAR datasets. And also QGIS have some toolboxes to basically do visualization of LiDAR point clouds and work a little bit with this. Also, a challenge in this case is the error estimation. We need to consider all the different sources of errors. And in this case, sometimes artifacts in the LiDAR surveys are very common. So we need to know where the errors come from. The estimation of the error for LiDAR sometimes is not that easy, and there is not a standard for this. So we need to find out how to do it and apply the corrections. In terms of computational requirements, it can require a large storage and computer processing and programming processing power. But depends on your study area and the amount of data that you have. And finally, we have GNSS. So GNSS is the general term for systems like GPS. And with GNSS, we can have the location of any point that has a device with GPS sensors, like this antenna in this example here. So this system has three main components: the satellites, the ground control stations that share information with the satellites to keep the satellites in a correct position in the orbit, and the receiver and user stations. So to have accurate locations, we need to have signals from at least 4 satellites. And in here you can see the GNSS station, an example of a GNSS station, and you can see that it has different components. So it has an antenna, it has a receiver, it has a source of power and batteries. But something important here is the foundation of the antenna. So each antenna has a different deep foundation depth. Some antennas are anchored at a few meters below the ground, but some are anchored at thousands of meters below the ground. In this case, we also have a few websites and initiatives that share in GNSS time series already processed, like the Nevada Geodetic Laboratory and the Jet Propulsory Laboratory, and CIRGAS for the Americas. And AirScope provides a lot of information about installation, at budgets, and basically educational and instructions information. We also have, like, in terms of processing data, there are some options, open source options to process the data sets. Personally, I always use the data depositions from Nevada Geodetic Laboratory. But if you are interested, there are options like Gypsy for processing the data. And some limitations in this case include time, because we need field work to install the station and to do maintenance. Also, economical limitations in terms that the cost of the installation and all the preparation can be high. So a budget from AirScope, I believe, is almost $30,000. And also we need communication with local communities and do a little more of basically to work with in the area. So we need communication. We need to know how is the access to the location that we want to know, that we want to use to install the station, and also we need to know to worry about the station safety. Still, we need GPS stations for validations and reference point. So this is a good, like, if possible, this is a good investment. So I am also going to talk a little bit about my experience using these datasets. So first, I am going to share with you a land motion in south of Lake Pontchartrain using INSAR and GNSS. And this is a study area. And you can notice in here many things. First, there are a lot of water bodies. We had 5 lakes in the area, and we have the Mississippi River going across the area. You can also notice that most of the south area here in purple is below sea level. So we need to know how subsidence acts in the area to know how relative sea level rise will affect this to the area later. You can also see that the city is protected by a levee system. It is protecting the area from waters from the lake and from the Mississippi River. And finally, you see that there are many falls in the area. Most of the falls are not moving, but some of these have estimates of recent sleep. Okay, again, I want to remind you that New Orleans is here in this red rectangle, and it is in part of it is on top of all of these sediments, and these sediments are still compacting, so we can have a subsidence caused by these kind of sediments. And also, this is the aquifer system in the area. So you can see here in the profile the 2-day prime in here, that the aquifer system is formed by many layers of clay and sand. And it's a complicated system because you can see that this layer has continuities and discontinuities. And also the communication between the water bodies and the aquifers occurs in some points of the Mississippi River, and also with some parts of the Lake Pontchartrain here. So in here we want to know how land motion varies across the study area, and how it relates with other factors like land use, surface geology, and hydrological cycle, and human activities in the area. So for this, we are using data from Sentinel-1. We are using data acquired between 2016 and 2025. And we are using ICE and MinPine to process the information. We are also using GNSS time series from NGL. And we are using many other data sets to know, basically to know the relations with each of these factors in the area. So I am going to show you some of the results here. First are the velocities across the study area. So in here you can see in the top image are the velocities. that range between minus 38 millimeters per year to 14.5 millimeters per year. And the figure in the bottom is the spatial coherence. The coherence of the results basically are a metric of how trustworthy is the interferometric signal in the area. So you can see that the points in the west in here are not as good as the points here in the east. It's not that these results are per se bad, but are not as good as the ones in here. And the blue points in here are covering the area that is urban area. This was expected because basically urban areas are very good reflectors, so are very good to study with INSAR. Now, if we go to the top image again, you can see this triangle, and this triangle is the reference point for my time series. And this triangle is the location of one GPS station, and so we know how it is moving. You can also see these diamonds in here across the area, and those are the locations of the other GNSS stations. And the color of the diamonds is basically the velocity estimated from INSAR between 2016 and 2025. So you can see that there are some diamonds that agree better with the INSAR results. For instance, this one and this one, the colors are very similar to the INSAR results. But there are some other diamonds that are a little more different here in the areas where the coherence value are slower. Smaller. So I want to take the opportunity to show you like some problems that I had before having these nice results in the top. So the top image is the one that I was showing you before, but the one in the bottom is the time series when an image, when an SLR image from INSAR. In this case, I include one image from 2015, and you can see the difference. We had more results in the areas that had more vegetation, but these results are not necessarily good. Actually, if you see the legend in here, most of all the results in this bottom image are very large. And if you compare with the estimates from GNSS, basically none of the GNSS agrees with the INSAR results. So probably this has many errors. Basically, this is because the 2015 image is causing more the correlation because there are two the time between the 2015 image and the first image in 2016 is too long. So we have the correlation errors because we have a large baseline. So just to take in mind like how you select the information that you are including in your time series. Now, if we go to the dominant soil factor, you can see here in the map that the river is surrounded by clays. And around the clays, we had mostly sand. The urban area is mostly covered by sand and clays. And the pits are surrounding the areas of the lakes. So if we go to this table, you can see that pit has the largest subsidence, but the number of points that lay in pit is very small compared with the clay and sand points. And what happens here is like basically the pit is covered by vegetation. So we don't have many points from vegetation because this is not a great surface to study with INSAR. Now, if we compare the clay and the mud, clay is moving faster than the sands, and that makes sense. However, if you see the error here, this is a standard deviation. Basically, all the soils are moving the same or very closely. So do you think that this is not a dominant factor causing land motion, but areas dominated by clay might need more attention in the future? Now, if we move to land use, we have different uses in here, and the ones in red or pink, these are basically urban areas that have different density of or urban development. We also have urban game. So most of the points from INSAR lie in these areas, and the rate of deformation in this case of these five classifications is -1 to -4 millimeters per year. And the coherence and the standard deviations are not that bad, at least compared with areas covered by natural and vegetation covers. So the natural areas are enclosed here in green. So you can see that the histograms show larger variations and a little more of basically different types of distributions. So we can say that land use is not a factor probably causing land motion per se, but we might need to pay more attention to natural and vegetated areas. The big rates can be caused by real change, but also we know that these areas can have a lot of errors, so we might need to pay attention with different methods. Now we know how velocities from INSAR and GNSS compare, but we can also basically compare the time series, how the deformation behaves over time. So in here you can see the time series from GPS, from GNSS in black, and from INSAR time series in red. So the left axis is showing the amplitude of the deformation from GNSS, and the axis on the right is showing the amplitude of the deformation of INSAR. So you might say like the shape of the shape of the signal, the shape of the deformation is kind of similar. But if you compare the amplitude of INSAR with GNSS, you can notice that INSAR is showing it has an amplitude 3 times larger than the GPS. The same with specific velocity rates. And now we move to the east. Sorry. If we move to the east, you see a similar behavior. The time series, the shape of the time series behaves similarly, but the amplitude of the signal is much bigger in Sentinel-1. So you might be wondering what is happening this, and we are also wondering that. So in our discussions, we had like two probable causes. The first one is that INSAR and GNSS are not measuring the same thing. So you remember that GNSS stations are anchored at different depths. So the station in here, DSTR, is anchored at a few meters below the ground surface, and this one, MRY2, is anchored at 2,000 meters below the surface. So basically, what happens is that they are measuring different things. But also we are thinking that we might have remaining atmospheric errors. We apply atmospheric corrections in the system, but we cannot, we need to verify that actually we don't have more atmospheric errors. We also have hydrological causes. So as you remember, the aquifer system in the area is very complicated because we have several layers of clay and sands, and the connections with the water, with the surface water, are not continuous. It occurs only in some parts of the lake and the river. So in this example in here, we have in the bottom left the time series from GNSS and INSAR. And in the bottom right, we have the time series of water variations in the Mississippi River. And the station to measure water variations is located here. So when we compare this, you can see that when water levels go down in the river, there is uplift. And when water levels go up, there is a subsidence in the GPS in the GPS time series. So maybe this is elastic, but this is something that we need to evaluate at our more local levels. So might be happening here, but not necessarily here in these areas. And now I am going to talk about a second example. In this case, I used LiDAR and INSAR to estimate motion rays in Baton Rouge. These results were already published, And here I want to remind you that Baton Rouge is located here in Pleistocene sediments, and these sediments are already compacted, so we don't expect subsidence from sediment compaction. Also, there are two faults in here, and these faults are normal growth faults, and they should be slipping down to the south. This is a sketch of the aquifer system in the area. And we know that between the two faults, there is a cone of depression caused by a large groundwater extraction. Baton Rouge is further from the coastline. It is like 100 kilometers there are like 100 kilometers between Baton Rouge and New Orleans. So here are some of the results. I am going to call northern block to the area between the two faults, and southern block to the area south of the Baton Rouge Fault. In this case, we only have two GNSS stations in the area, and both are in the southern block. So this was a little bit challenging to basically to validate the results, but still these two GPS stations have a good agreement with the results from INSAR. And in here you can notice that the northern block, the area, this area between the two faults, is subsiding faster than the area south of the Baton Rouge Fault. So you can also notice that the Baton Rouge Fault is a boundary between the subsidence occurring in the two blocks. And when we do the analysis between LiDAR with LiDAR data, for this we use two surveys, one taken in 1999 and the other one taken in 2018. And we found a similar behavior with more subsidence in the northern block than in the southern block. So what happened in here is like when we compare with the geological studies made before, basically our results are contradicting the long-term displacement, because in the long term, the Baton Rouge Fault is slipping with a rate of 0.04 millimeters per year. But we are actually finding that the northern block is subsiding faster than the southern block, so this is contradictory. So to study this part, to know what is happening, we start to study human activities in the area. So previous studies found this cone of depression between the two faults. And when we compare the location of the cone of depression caused by a ground water extraction, mostly in the deeper aquifers, with our results, we see that most of there is more subsidence in areas that have the cone of depression, and subsidence decrease in the southern block, in the southern and in the southern wall block. We don't have that much groundwater extraction. So, well, these are basically the summary of my talk. I know that I said like I use a lot of concepts, and I was talking about land deformation and large geodetic datasets, but I hope you well keep in mind these points. So in terms of land deformation, basically we have an spatial and temporal components. So land deformation can vary in very different scales in these two components. Also, the origin of the processes can be natural or human, and the total land motion is a product of different processes happening at different depths. Quantification of land motion is important in coastal areas to know the effects of relative sea level rise. Also, in terms of the large geodetic datasets, we need to understand what can do each method. And in the case of LiDAR and INSAR, these ones have a great spatial coverage, but they have limitation that we need to work along the processing. And we need GNSS stations to validate information from geodetic and remote sensing results. In the case of Louisiana, there are the land motion varies a lot, and in the region, we think there are many processes that are occurring simultaneously. So we need to do a more local assessment. And for Baton Rouge, a groundwater extraction dominates the land deformation in the area, and the Baton Rouge Fault divides the area in two areas of human-controlled subsidence. So that is everything from me, and thank you for your attention. Let me know if you have any question.
Thank you, Carolina. It was very nice talk. There were lots of pointers, and I'm sure there will be quite a few questions. We have two, in fact, already. One of the first question is from Murtaza Nadeem, and he's asking that in previous slide where you mentioned about building foundations, so on what level does subsidence begin, like how deep in ground, or in other way, what shows be the foundation depth at least? I guess this is related to the introduction that you started with, right, in I think the first couple of slides.
Yes, I think this one. So to what level does subsidence begins? Basically, subsidence occurs at any level at any deep below ground surface. So something that is happening at very shallow, a few centimeters below the ground, is going to cause subsidence. But something that is happening 2 meters below the ground might also be happening subsidence. So happens at all depths. How we see it on the surface depends on basically of the geology and the soils and how basically they respond. So we need basically to know, to be aware of what we are measuring and what can we measure, because sometimes some processes take time to actually reflect the substance in the surface. What shows the foundation depth? I don't understand the second part of the question. What way shows the foundation depth? If I understand this part, basically, like if we know the foundation, for instance, in the case of this building, let's say that this building has a foundation of 100 meters, because we can. So it's going to show everything that is happening below the 100 meters foundation. I hope that answered the question.
Right, so there is another question related to Snafu plugin, that instead of Snafu plugin in ESA, is there any other unwrapping any other software? I think the person is asking about unwrapping interferograms in open access.
Yes, I think there is another one installed in MinPy. Sorry, I don't remember the names right now because I tend to use Snapu most of the time. But I think there is another option. Personally, I use Snapu because in general it has good results for unwrapping interference. But yes, if you go to MinPy documentation, there is another option.
Yeah. So for the listeners, MintPy is also a time series interferogram inversion algorithm, which is also in open access. Right. So the next question is there any robust method in calculating such subsidence with large data set from radar, for example, deep learning approach?
Well, in terms of methods, we have PSA, persistent scatter interferogrammetry, and the other one is SBAS, is small baseline, small baseline. And this is the only thing that we need to know. So those two are the ones that we know. Now, how they are applied depend on basically on the software. I tend to use mostly a small baseline that is integrated in MinPy. And deep learning approach, I think there are deep learning approaches. I haven't used them. I per se try to use the MinPy approaches because they had been used many times. So part of my experiments are not to try new methods, but to apply these methods to an area. So in the deep learning approach, I cannot say, but there are several methods.
Right. So the next question is, your INSAR and GNSS time series show persistent velocity offsets. Does this discrepancy primarily represent remaining atmospheric noise, in INSAR or real differential motion between the shallow surface and the deeper anchorage?
We are trying to find out. Um, well, I was saying in that slide, like we are trying to find out what are the causes of these differences, because we can see all these differences, like of 3 times of the amplitude, more or less, difference between the INSAR and the GNSS. So we need to know if it's atmospheric, maybe effects that were not removed before. So we are working on that.
Right, right. We just have another question here. Why the results for 2015 to 25 are not good as compared to 16 and 25 for Louisiana motion?
Well, when I was doing the 2015-2025, I include basically the difference is only one image, one SAR images. So the things like the time between these SAR image from 2015 and the other images in 2016 are in, I think, a few months, let's say 6 months. So there is a large, is a long time between the SAR images. And probably there are a lot of the correlation errors in here. So yeah, basically the correlation caused by a long time between the images.
So you mean to say that even a single bad
Yeah,
interferogram can really screw up your deformation time series?
yes. Actually, like
Yeah.
one SAR image in this case, when I was creating the
Yeah.
interferograms between this SAR image and the other SAR images, the errors came from there.
Right, right. So roughly speaking, for the entire time series of these 10 years or so, it was, what was the maximum spatial baseline you had? Um,
A few days, I think, like between, I was trying basically to use all the SAR images that I found with this period. So maybe 12 days between acquisitions.
for the Sentinel-1, the temporal baseline, and the spatial baselines you think were like within plus minus 50 meters or 100 meters?
I think maybe like 40 meters.
Yeah,
Yeah,
yeah. So you chose the small baseline subsets.
yes.
Right, right. We still have a few minutes for further questions. So if there's any other question from the audience, please feel free to chip in. In the meantime, I, of course, have a number of questions and queries from my side, because I was particularly intrigued that you showed a lot of interesting results on varied land cover usage. So you were discriminating between different soils also, that this particular soil behaves. So in your analysis, different like peat and clay and so on. So the difference in their compaction or let's say the vertical motion, it was significantly different. I couldn't get the take-home message from these interferograms that you do think that they were really different?
I don't think so. Well, in here I am
Hmm.
comparing, basically what we did was like to take all the points, for instance, in clay in the pink areas in a classification. I
Hmm.
Same with peat and with sand. So they are not that different if we consider the standard deviation, because you can see like the standard deviation is big in any case, so they overlap a lot. Also, the distribution in the histograms is kind of similar, and maybe some has maybe a shorter range of land deformation velocities.
Hmm. Yeah, yeah, might be quite similar. And in one of the slides, I think it was 26, you were showing this periodic rise and fall of the gauge level, and you
Eh,
also related it to the vertical motion that you were observing in the interferograms. So I think
eh,
it was, yeah, it was this slide, I think, perhaps, or the next, maybe. Yeah, yeah, here. So in the bottom left, here so there's quite a large periodicity here in the GNSS loss rate.
Mm-hmm.
And you think this was significantly related with the water levels?
Yes. Well, let me go to this one. So,
Yeah, these ones.
for at least for this station, it seems to relate with the water levels in the river.
Mm.
Something that I didn't show today was another study that I was making about seasonal deformation in Baton Rouge. So in that case, basically what we could prove was like that at seasonal scales, it depends on basically on the Mississippi River, on the changes of the Mississippi River. And basically you could see the variations of like motion, like the response of the motion on how well the river was connected with the aquifers. So I'm going to use this image just for reference.
Hmm.
So in Baton Rouge, we have the river here. So these areas in here were responding very well to the changes in the Mississippi River. And actually, they were not responding in an elastic way, but in a poor elastic because the aquifer in this part of the area is unconfined. So they were responding immediately. But when compared with areas close to this part that I am pointing, the response was much like is lower, and in some cases was not related. So yes, seasonality I think is related to basically to hydrological processes, but sometimes depends on the closeness between the location that we are looking and the water body.
Right, right. And would you also comment on the atmospheric corrections that you applied here? Any specific thing that you had to do, or you think the usual way it's done in MintPy or Pi APS based estimates were good enough?
Well, to do atmospheric corrections, I am using the ERA5 model. It is basically pre-installed in MinPy, so it downloads the data and knows how to do it. I think they are not, I'm not sure at this point if they are enough because we have a lot of different, like a big difference between GNSS and INSAR. And the difference in amplitude is almost the same across the area. It's not something that is happening just in a piece of the area. So we need to check. We need basically to know what other maybe weather effects we are looking at.
Yeah, it's on the whole, this is a very nice work, very comprehensive, but quite a lot of validation done with different tools or technologies, GNSS, sometimes INSAR, and sometimes LiDAR. So I think it's really, really nice. So I think we are close to our finish line here. So any final question from the audience? If not, then I would like to thank Carolina for giving us her valuable time. And I also thank all the participants from all across the globe who joined us today for this webinar, which will be the last one in the 2025 series. So I wish everybody happy holidays. Have a great time. And from our side, see you in 2026. And thank you, Carolina, again. Have a good day.
Thank you for the invitation. Thank you, everyone. Bye.
Bye.